So since we've looked at logarithmic functions, now let's look at its inverse. We're going to look at exponential functions. And today what we're going to look at is only exponential functions, e to the x, not any bases other than the natural base. So the inverse function of e to the x is the natural log. So they are inverse functions of each other, remembering if we can convert from exponential to logarithmic and logarithmic to exponential, they are inverse functions. So since the natural log of x and e to the x are inverse functions, when we substitute the inverse function into the other function, so I have the L of n function and the e to the x function, if I substitute an inverse into its inverse, so they're inverses, I end up with x. They are undoing functions. So if I substitute in the natural log of x for x in e to the x, those are inverse functions. I'm substituting the inverse function in for x, and it should simplify to x. So what is the derivative of e to the x? So for this, we don't know how to take a derivative of an exponential function, but we do know how to convert an exponential function into a logarithmic function, or we know how to do logarithmic differentiation. So I'm going to do this one using logarithmic differentiation, and I'm going to take the natural log of y and the natural log of e to the x. Well, as we've seen up above, the natural log of e to the x, I should know what that is, but I'm going to go the other way also. We saw that when I substitute the inverse into the function, I should get x, but I can use properties of logs also to show you that this is true. So the exponent comes out front, and the natural log of e is just, this is asking what exponent do I need to raise e to get e? Well, this is just 1. So what I see here is that the natural log of y equals x. So now I'm going to take derivatives. So the derivative of the natural log of y is the derivative of y divided by y. 1 over y is my derivative of natural log, and then chain rule gets me the derivative y, and the derivative of x is 1. So now to solve for y prime, I multiply both sides by y, and I want this in terms of x, not in terms of y. So when I substitute back in, y was equal to e to the x. What I see is that y prime is e to the x. So what that tells me is that the derivative of e to the x is e to the x. If I'm being honest, that's probably the easiest derivative we have ever taken in this class. So the derivative of e to the x is e to the x, as we have shown with logarithmic differentiation. So now let's practice that in regular settings. So if I want to find the derivative of f of theta, so if I want to find f prime of theta, it is not just e to the x. It has a function in it. So I am going to be using, the chain rule here, e to the sine of 5 theta. So the derivative of e to the x is just e to the x. So the derivative of e to the sine of 5 theta is just e to the sine of 5 theta. And then I need chain rule. So then the derivative of the inner function, what is the derivative of sine? The derivative of sine is cosine of whatever. And then I still have one more inner function. The derivative of 5 theta is 5. I do not have to simplify this if I want to write it in an order that's a little easier to see. That would be 5 times the cosine of 5 theta times e to the sine of 5 theta is the derivative. If you would like to try to find the derivative of f of x yourself, you could pause the video and try this. But let's look at this derivative. So I'm going to rewrite this as e to the x to the negative 1. That will make it, I believe, a little easier. So f prime of x, the derivative of e to the x is e to the x. So the derivative of e to anything else is just e to anything else times the derivative of the inner function. So my inner function is x to the negative 1. I bring the negative 1 out front and subtract 1 from the exponent. So if I simplify this, I have e to the x to the negative 1 divided by, or times negative 1 and divided by x squared, because the x to the negative 2. Let's try this one. F of x equals e to the square root of x. If you want to go ahead and try that one, go ahead. So I'm going to rewrite this as e to the x to the 1/2. So f prime of x is going to be e to the root x, and then chain rule. I bring the 1/2 out front and subtract 1 from the exponent, which means what I have here is e to the square root of x times 1 over 2 root x. So what that gets me is e to the root x over 2 root x. Here's where some kids get confused. What if I said f of x was e to the square root of 2? What is f prime of x? Well, this function is a constant function. It does not have a variable in it. And so the derivative of a constant is 0. But if you don't believe me and we want to try to use the derivative with chain rule, the derivative of e to anything is e to whatever that is, and then multiplied by the derivative of the inner function. So the derivative of square root of 2 is just 0. So I get e to the root 2 times 0 still gets me 0. But you should have recognized that is just a constant, not a function with a variable. So let's try one more. See if you can do this one. M of x equals e to the tangent of 3x squared minus 2x plus 10. So pause the video, see if you can take that derivative. So m prime of x is derivative of e to anything is e to the anything. And now I'm working on my chain rule. So then the derivative of tangent is secant squared of whatever the tangent was of. And then I have one more inner function. The derivative of 3x squared minus 2x plus 10 is 6x minus 2. And I would not make any attempts to simplify that. I would just leave it that way. Hopefully you did well with that. So now let's look at integration. If differentiation is easy, integration should also be similarly easy. So if the derivative of e to the x is e to the x, then when I undo it, when I go backwards, the integral of e to the x dx has to take me back to the function. If this is the function and this is its derivative, when we are integrating the derivative, we should get the original function plus c. So if differentiating it, e to the x is an easy derivative, then integrating should also be relatively simple. So what we're going to be focusing on now is the thing that's going to make this most likely more difficult would be u substitution. So in this case, my inner function is x cubed. So if I let u equal x cubed, I'm trying to integrate x squared times e to the x cubed dx. So then du is 3x squared dx. Most of you prefer the 3x squared, so I need a third. So this is going to give me 1/3 the integral of e to the u du, because I see my du in there with my dx. So now I just have 1/3 e to the u plus c, and I can then substitute in for the u, x cubed plus c. I have several of you that are currently skipping this step, and once you know what the integral will be, also substituting in for the u at the same time. That is completely acceptable. Feel free to do that. So now, what about e to the x over 1 plus e to the x dx? But now I'm integrating it over an interval. Okay, so we have a couple things here. The first is my u is going to be the 1 plus e to the x. So du, derivative of 1 is 0, derivative of e to the x is e to the x dx. So what I see right here is that my du is right there. So I'm going to deal with that first. So my integral now is 1 over u du. Now, I had end values, so those need to be converted to u's. So u of 1 is 1 plus e to the first. So this becomes 1 plus e up here, 1 plus e. And then u of 0 becomes 1 plus e to the 0. And e to the 0 is 1. So 1 plus 1 is 2. So this is 2. So now when I do the integration, 1 over u is the natural log of the absolute value of u, evaluated from 2 to 1 plus e. So now I go natural log of the absolute value of 1 plus e minus the natural log of the absolute value of 2. E is approximately 2.71. Plus 1 is going to be 3 point something. So this definitely does not need parenthesis, or does not need absolute value. And natural log of 2 is a number, it's always positive. So I can use properties of logs to write the integral as the natural log of 1 plus e over 2. We also need to review a little bit of solving exponential and logarithmic equations. So to solve an exponential, e to the x, we are going to, the way we did it in pre-calc, you can either take the natural log of both sides and then the natural log and the e to the undo each other, or you can do the conversion from exponential to logarithmic. So this means ln of 5 is going to equal 2x plus 1. So what that gets me is now a number equals 2x plus 1. I can solve this for x. If we remember, I will remind you, e to the x equals y if and only if ln of y equals x. So basically we are converting, because the log equals the exponent, we are just converting. You can do that in your solving process. So now I'm going to subtract 1 from both sides, and then I'm going to divide both sides by 2. You can put the -1 on the back side, but oftentimes we get confused later. Is that inside the log or not? And so I like to write it out front. And then if we need an approximate, we can plug that into the calculator. You should get about 3.3047. This should be coming back to you. We covered solving logs and exponentials in pre-calc. So here's the other way. So this is natural log is log base e of 3x plus 5 equals 7. To solve this for x, we are going to convert from exponential, or we convert from logarithmic to exponential. So the exponent is 7 and the base of natural log is e. So e to the 7th is going to equal what is inside our natural log. And e to the 7th is just a number. I can't get it exactly without just saying e to the 7th, but it is just a number. So I'm going to leave it as e to the 7th. I'm not going to approximate until the end. So now when I solve, I have e to the 7th. I'm going to subtract 5 from both sides, and then I'm going to divide both sides by 3. That is my exact solution. And then I can approximate by plugging that into the calculator. When you plug this one into the calculator, if you don't make it a fraction, make sure you put the numerator in parentheses. Otherwise, the calculator will only divide the 5 by 3 and not the entire numerator. And when I type this into my calculator, I should get approximately 3.63.8 and a few sevens. So just a quick reminder of solving exponential and logarithmic equations. So now we're going to just do a couple more examples and be done with this. So this is going to be a product rule because I see a product. So when I do this derivative, I need to remember the product rule. So f prime of x is the derivative of the first. Sorry, dyslexia. I just about did it again. The derivative of the first times the second. Oh my goodness. Plus the derivative of the second is going to be e to the x cubed times the derivative of x cubed, which is 3x squared. Derivative of the second times the first. So I should be able to simplify this a little. This gives me 2x times e to the x cubed, and this gives me 3x to the fourth times e to the x cubed. You would not have to do this, but in case it showed up on a AP exam for a multiple choice, since I have e to the x cubed in both of these terms, I could technically factor that out. May not be required on free response problems, but so that you could recognize it on a multiple choice. And then let's try this one. This one is going to involve a quotient rule. If you want to try that yourself first, go ahead, pause the video. So to find g prime of x, I want quotient rule. So I have low d high. So the derivative of the numerator is e to the cosine x times the derivative of the inner function chain rule. Derivative of cosine x is negative sine of x. I will remind you that if you are writing negative of something, you need to put it in parentheses if it's multiplied by something else. A lot of you are getting lazy and leaving those off, and now you have a subtraction problem, not a multiplication problem. So I have low d high. So here's my low and high. So I have low d high minus high d low. So high is e to the cosine of x times the derivative of the denominator, which is 5, all over low, low. And you can leave that one there. So we have an example of product rule, and we have an example of quotient rule. So now let's look at a slightly more complicated integration that is going to involve u substitution. So I'm going to suggest that you pause the video and attempt to do this integration on your own. So I'm going to let u equal cosine of x. So du equals negative sine of x dx. And if I'm looking for du in the function, I need the negative on the sine of x, which is going to require the negative out front. So now I can see my du. So I have the opposite, or the negative, of the integral of e to the u du, which is going to get me the negative of e to the u plus c, which gets me the negative of e to the cosine of x plus c.